السلام عليكم. يعطيكم العافية. We will review lecture 10, which was the previous lecture. We spoke about compaction. Remember, we have two types of compaction tests. Okay? The first one is standard Proctor compaction test. The other one is modified Proctor compaction test. Now, the difference between them is the weight of the hammer, 5.510, the height of the free fall distance, 12 inches, 18 inches, how many layers of soil we put in the mold, 3 here and 5 there, and number of blows, 25 fixed in both experiments. From this experiment, we will draw the compaction curve, which has a relation between gamma D maximum and W optimum moisture content. And we see that we will have such kind of curves, which gives us a peak value, just one peak value, okay? Peak value. This is what we are looking for, peak value, okay? The optimum moisture content that gives us gamma D maximum. Now, before it, we will have weaker soil. After it, we will have weaker soil. So we are looking for the maximum strength. The maximum strength is the maximum unit weight, dry unit weight. So this comes only with one W, with one water content. Any additional water will make the soil weaker. Any less water will make the soil weaker. So we are looking for just one number. Now, this is, we call it ZAV, right? Zero air void. This is not a line. This is a curve, but just part of a curve. Part of a very big curve, which represent zero air void. All the voids are almost exterminated, okay? We don't have voids. As if we compacted the soil to reach a state or a condition where we don't have voids. Okay. Now, how to reach W optimum and gamma D from the test, right? But we will get them. Now, I told you that optimum moisture content, you have to think of about 3 to 15% only. We don't have to think of too much water. It's just little water. And we knew why the strength increases first, then decreases, right? I explained this in the previous lecture. Now, so it should be between 3 and 15, something like that, okay? Now, how to use this result in the field? At the end, I will do the experiment, or I will compact the soil in the field to reach W optimum and to have at that time maximum strength, right? So how I have to do this? Now, I will take W optimum, okay, and go to the field, put this kind of water, this amount of water or little less, and then compact the soil there using rollers. You know, we have rollers to be used, different types and shapes. We will talk a little about them. Okay, and then we will compact the soil. Now, how I can guarantee that I reach the gamma D maximum? By making what we call it field compaction tests. We have several tests. Rubber balloon test, sand cone test, okay, or even by using nuclear device, okay. So we have different field compaction tests to do, and we will continue doing that until we reach how much? 100% accuracy. Especially when we have some important projects. What kind of important projects you think of? Important projects like, for example, runways. Okay? Runways. We cannot allow ourselves to have even 99% of gamma D maximum. We have to reach 100%. Okay? Because in the runways, I don't want to have accidents with airplanes going down, then the runway is going down, up and down because of some voids, okay? So we continue doing the test until we reach 100%. okay, until we reach gamma D maximum. Runways, railways, highways, okay, important highways. These are all I should reach 100% accuracy. I mean, I have to reach gamma D maximum exactly as in the lab. Okay, the same figure that I have it in the lab. Okay, now I will not discuss here, but if you will study advanced soil mechanics, we will speak about the equipments and instruments that we use in the field for compaction. We have rollers, rollers, madahil, okay, all types of rollers. Some of them smooth drum, which has very smooth roller at the beginning. Some of them, they have 6 or 4 small tires, if you remember, if you saw such things, okay, at the beginning. Some of them have this kind of roller, but with pieces like this. We call it sheep goat or sheep foot, okay? So there are several of them. And what to use where, this will be discussed in advanced soil, okay? In advanced soils, we will tell you what type to be used in what circumstances, okay? It's not a matter of, please bring the biggest or the heaviest of them and use it. No. For sand, there are special type of equipments. For clay, there are different types, okay? For saturated clays, it's not recommended to use this, but it is recommended to use that, okay? All of this will be discussed in advanced soil mechanics if you studied advanced soil mechanics. But what you need to know is that from the Proctor, from the standard Proctor or modified Proctor, I can calculate the energy, okay? The energy. And from that energy, I can go to the machines, okay? And from then I can choose which kind of machine I will use, okay? We will end up with this in speaking about compaction, and we go now to another subject, another chapter, which is soil-water relationships. Okay, soil-water relationships. Or it can be written like soil permeability. Permeability nafadiyya. Soil permeability. Soil-water relationships. Let me say something at the beginning. Understanding soil is not easy. Although we studied all what we studied until now, but in fact, understanding soil and dealing with soil is very difficult. And it will be more difficult when this soil is wet, is saturated. It is very difficult to deal with soil alone. So how it will be difficult when we deal with soil and water? It will be more difficult, okay? Actually, understanding what kind of relation between soil and water is very difficult, and the only way to do so is to go back to understand water alone, okay? I mean, to understand what is fluid mechanics, okay? You studied something in physics, right? About fluid, about laws of fluids, okay? So what we did, we based our knowledge here on basics of fluid, okay? And we studied about Bernoulli, you know Bernoulli. We studied about Torricelli. We studied about some of those scientists who did something in the field of fluids, okay? We took their knowledge and applied it to soil, and we made a combination that is soil-water relationships. Okay, that was the only way to understand it. So we will begin with some physics, some fluid. Okay, not very difficult. Don't be afraid. Soil-water relationships or soil permeability. Suppose I have a pipe like this. This is a pipe. Okay, this is a pipe, a hollow pipe. Okay, open from both sides. Okay. A hollow pipe that is open from both sides. It has a cross-sectional area A. It has a length of L. Okay? Are you ready? Okay. Now, I have a hollow pipe open from both sides. That pipe has a cross-sectional area A and a length L. Okay? And I allowed water to flow from inside the pipe. Okay? So I will have water inside. This is, we call it inflow, right? And this water, of course, will come here. That will be outflow. Okay? And it is obvious that inflow will be equal to, unless I have losses. Okay? I don't have losses here because it's a short pipe. Okay? So I don't have losses because of joints, because of any problem. Okay? So the inflow amount is equal to the outflow amount. Right? Are you with me? Okay. So this pipe, we had water going through it. So we have inflow and we have outflow. Okay? Now, of course, you can understand that sometimes the water that will pass through this pipe, it may not fill the pipe, right? It may be like, for example, just part of it. It covers part of it, right? But suppose that we have water filling all the pipe. So I can say that the cross-section of the water is the cross-section of the pipe, right? Okay? Are you sleeping? Not yet. Okay. Now, we will use this to do some calculations. Remember this drawing, and we will go for some calculations. Now, can I say that Q, which is the collected amount of water, okay, I put the picture here, you will see, I put here a container, and collected water here, okay? After 10 minutes, I collected Q, right? What is Q? The collected amount of water in certain time, okay? It's a volume. Meter cubic, of course, per time. Not per time here, but I collected it per time, but this is an amount, okay? This is an amount. It's just volume. But I collected it in 10 minutes, etc. So I can say that Q equals to Q small multiplied by time. Okay? What is Q? Q is flow rate. Okay? This is what you said, that speed per time. Okay? So it is, can I say that Q, amount collected of water, equals to flow rate multiplied by time, right? In 10 minutes, I will collect more than what I can collect in 5 minutes, right? So time is a factor, okay? And the flow rate is a factor also, because if I am pumping with a flow rate of, for example, 10 meters per minute, it's not like pumping pumping with a speed of 20 meters per minute, right? So Q and T. Okay? So flow rate multiplied by time, okay? Okay. Now, flow rate, let us use what we say here. Now, flow rate, Q, can I say it is velocity of water multiplied by the cross-sectional area, right? So it is velocity multiplied by cross-sectional area A. So it's V multiplied by A. Flow rate equals to velocity by cross-sectional area, right? Now, if we have a pipe and water goes through it, what are these factors that affect the velocity? The velocity of water passing through the pipe. What are these factors? Cross-section, one factor. Okay, I put it, A. What else? The pressure, the initial pressure. Suppose the pressure is 0, okay, free fall. What else? What is Z? Okay, elevation. If I put the pipe like this, it's not like putting it like this, right? So if the pipe is sloped, okay, how high is the slope? How greater the velocity will be, right? Okay. So one of the factors that affect the velocity is the slope. The slope. That's why we said is V proportional to I. V proportional to I means when I is greater, V is greater. When V is greater, I is greater. When I is smaller, V is smaller. Okay? V is proportional to I. I, we call it hydraulic gradient. Hydraulic gradient. What is hydraulic gradient? It's delta H divided by L. So we are talking about the slope, right? The elevation difference divided by the length. Delta H over L. Okay? So this is hydraulic gradient. So once I is greater, the velocity is greater. Once I is smaller, then the velocity is smaller. Okay? So V is proportional to I. This is very important. V is proportional to I. But I don't like this kind of relation. I like it to be fixed with numbers. Okay? Now here comes one of the most important people that you should remember his name. In soil mechanics, there are certain names that you should remember always. They are very important. The first one I will tell you later, at the end of the semester. Okay? The second one is Darcy. Okay? Darcy. The third one is secret now. The fourth one is unknown now. The fifth one, your name. Okay? You may forget it, but don't forget the first four. Okay? Now, Darcy, he's one very famous person. Now, he put his law. That's we call it Darcy's law. You should remember this. Okay? Darcy's law. Darcy's law. Darcy's law, he said that V equals to K multiplied by I. So he translated this V proportional to I to put it in an equation that says V equals to K multiplied by I. V is velocity. I is hydraulic gradient. So what is K? K is a constant. Okay? A constant that's called coefficient of permeability. Coefficient of permeability. معامل النفاذية. You just tell me K and I will tell you everything about the soil-water relationships. Okay? So we ended up here by just asking ourselves a question. What is K? Tell me K, I'll tell you everything. Okay? K, coefficient of permeability. Okay? Coefficient of permeability. If I knew K, I will know everything about the soil. You just give me K. You remember I told you once, you just give me PI plus this index. I will tell you everything about the soil. Remember that? And you tell me K, I will tell you everything about the soil-water relationships. The K factor, the key word is K. Okay? Coefficient of permeability. But before that, let us do some mathematics. Okay? You like mathematics. Remember the first equation I put Q, collected amount of water equals to Q flow rate multiplied by time. But I knew that Q, I said that it is V multiplied by A, right? So I put it VA multiplied by time. But I knew that V is KI. I just wrote it now. So it's KIAT, right? And I know that I is delta H over L. So I can write Q equals to K delta H over L multiplied by A by time. These relations, I can use them. Okay? These relations, I can use them. Okay. Now the question is, how to find K? That is my question. How to find K? By the way, you just give me K, I will give you everything about soil-water relationships, right? So how to find K is our job. How to find K. By the way, if you look to your textbook at page 61, you will find a table that's table 4.1. Okay? And there are several numbers for K. Okay? K when I have sand, when I have loose sand, when I have dense sand, when I have clay, when I have gravel, when I have, etc. Okay? There are different Ks. Just to have an idea, let me compare between two figures. If we have clean sand, okay? Clean sand. So K may reach 1 meter per minute, even per second, 1 meter per second, okay? Are you with me? K in sand, in clean sand, I have clean sand or gravel. K, which is permeability, it may reach 1 meter per second, means that water can go through the soil 1 meter per second. Okay? This is K. But if I have clay, especially if I have bentonite, remember that troublemaker? Okay, bentonite. It may reach 0.00001. Actually, it may reach centimeter per second or even per minute. You see how much is small? Even it may reach 1/10 to the power -7. Okay? So that's why, that explains why I have problems always with clay if I have water, not with sand. In sand, the water will go very smooth and quickly, and I will finish this problem. But in clay, it takes very long time. It takes very long time. Why? Because permeability is very low. Okay? This is an idea, you should have it in your mind. Permeability in clay is very small. Permeability in sand and gravel is so as greater the particle size, K will be high or K will increase. As smaller the particle size, as smaller the coefficient of permeability K. Okay? That's why we have problems with water in clay more than in sand. In sand we don't have it. In clay we have it. Okay? Now, let us see how to find K. How to find K. Because, okay, the table is there, then let us use it. No. That's very general. That's very general. It says that, for example, for clay, it may range from X to Y. But what number of it? I cannot say. So I have to do this experiment always for every soil when I'm dealing with water. If you are designing a dam, if you are designing a water tank, if you are designing a pool, if you are designing a basin, if you are designing anything that relates to water, then you have to do a permeability test. By the way, permeability test is your test after compaction. Okay, you will do it in the lab here. Okay, you will do it in the lab. Now, how to find K? Three main methods. The first one is empirical methods. Empirical methods. What's empirical? What's the meaning of empirical? Experimental. Good. Empirical means there are relations that is done by experiments, by tests, etc. Anybody figured out some kind of relations by trials. By trials, I reached this relation. By trials. Whether they were experimental or something else even. But by trials. So these are empirical methods. There are several empirical methods. One of them is written in your book, is this one. K equals to C multiplied by D10 square. What is D10? Good. Remember, I told you to put it down and write it and remember it. Effective grain size, the diameter at which 10% of the sample will pass in the sieve analysis. Okay? D10, effective grain size. So I will take that diameter in millimeters, multiply it, okay, and then multiply it by C. What is C? C constant, okay? C constant. C constant. Ranges from 100 to 200. C constant ranges from 100 to 200. Do you think that is useful? I mean, if C is 100, it's like 200. So, let me tell you something. You can use any empirical relation, but, and you put some lines under but here. That means you have to read the assumptions before using that relation, okay? Did you understand that? You can use any empirical relation, but you have to read the assumptions that over which this relation was based. It's not, you see, what they do here. Those people who work on that issue, they do experiments. During these experiments, they put limitations and assumptions. Assume sand is clean. Assume there are no gravels. Assume that water is so and so. Assume temperature is so and so. Assume viscosity is so and so. Then neglect all these kind of things and put all these kind of limitations and then write down a relation, okay? Can you apply this to something else? For example, if he was doing it on sand, can you apply it to clay? It's written that it's not applicable for clay, so you cannot use it. That's why don't use any equation, any relation before reading the assumptions and limitations of that equation, okay? Now, so this is one of the ways that can be used. It's written in your book, by the way. K equals to C multiplied by D10 squared. And it has limitations, it has assumptions, so I don't like it. And I don't use it. And even I don't look at it. I remember it just when I explain it to students. Okay? Now, there is another equation, but that's too long. Too long. It's called Cozzini-Kármán equation, based on two authors, Cozzini and Kármán. Okay? Cozzini-Kármán equations. It's a very long equation, and you end up with, I don't want to say it, but maybe a silly equation. Okay? Or a useless equation. So, empirical methods. What else? Also, there are certain or several other equations, but we don't want to spend our time reading or writing or understanding equations that are limited, that are useless, that are very vague. You know vague? Vague. loose. مساحتها واسعة من 100 ل 200. Vague. Vague. It's not fixed. I want to deal with fixed. Okay? So I don't like the empirical methods. I will go to lab methods. Why we have laboratories? Just to do lab methods. Okay? And we will have two tests. Okay? Lab methods. The first one is called constant head permeability test. Constant head permeability test. This is the one, by the way, you will do in the lab. Okay? This test you will do in the lab. Constant head permeability test. From the beginning, I'll tell you, this is used for sand, for gravel, for granular material, for coarse material. Okay? It is used for coarse material, for granular material. This is an easy drawing for it. I will have water tank here. Okay? Then I have a cylinder in which there is soil, the soil sample. Then I have a pipe, and I will end up with another container or tank. Okay? Now, water is here. Okay? Now, this is closed. What I will have? If water is here, then, of course, everything under it is filled with water, right? So, water is covering all or filling all this part, right? If I open this, water will go through until it will go out from here, right? So I will let this going on until I will begin the test. When I will begin the test, I'll close this, everything, water is already there, and then immediately I will put water here. I will leave this open. Okay? I will put water here and let the water go through the soil sample until it will be collected here. Okay? Now remember that this distance is fixed, right? Right? It is fixed. The level will continue fixed. The level will continue constant, right? Because water will continue flow in the tank and flow out of the tank, but still continuing process. Continuing process, that means distance is fixed, right? That's why it's called constant head. By the way, the word head in water means level, right? Irtifa, level. When we say constant head means the constant level. And it is obvious, constant. You see? Water head will not change. It is fixed with a distance h. Okay? Now, if the cross-sectional area of the sample here is known, it is known, by the way, it's written on the cylinder in the experiment, in the laboratory. And if the distance from here to here, from the beginning of the soil to the end of the soil is known, it is L. You see? L is the length of the specimen, of the sample, right? L is the length of the soil. A is the cross-sectional area of the sample because it's the cross-sectional area of the pipe. And H is known, okay? And I began the test, 1, 2, 3, begin, okay? In 10 minutes, I collected Q, right? Okay? In 10 minutes, I collected water. That water, I will call it Q. It's a volume, right? So I have Q, I have T, I have L, I have A, I have H. Remember that equation? Remember that equation? Here? You see? I will use it now. Q, remember that equation. Q equals to K multiplied by delta H over L multiplied by A multiplied by T, right? So from it I can find K, coefficient of permeability. What it will be? K equals to Q, I know it, multiplied by L, I know it, divided by A, I know it, divided by H, which is fixed, the difference, divided by T, the time of the test. Very good equation. Let me write it again. K equals Q. Guys, Q in meters cubics, right? Concentrate with me, please. Q in meter cubic, right? Or in whatever, volume, multiplied by L. L meter divided by A meter square divided by H meter, right? Divided by T minute or seconds, okay? Let us take minute. Now, let me say meter by meter, okay? Meter square by meter cubic, then what is the answer? Meter per minute or meter by second or whatever. That is coefficient of permeability. Okay? K, the units of K always is meter per minute, meter per second, whatever. Okay? So I can use this K equals to Q multiplied by L divided by A H T. Okay? In your textbook, there are some problems solved. You can read them. And there are some problems needed to be solved. So you can try them, okay? And if you have any question or any problem, you can talk to me. Okay? Again, let us look at the inflow, outflow. The distance is fixed. That is H. Okay? That's why it is called constant head permeability test. Cross-sectional area A, length of specimen L. At time T, we collected Q, volume. Okay? From this, we can find K. Very easy. It takes around 10-15 minutes. You will finish the test. Okay? It's very easy. But that test can be done for sand. Why? Because you remember, if you bring sand and you put water, immediately water will go through. In 10 minutes, you will collect a good amount of water through sand. But in clay, you may wait 1 hour to get at the end 1 drop or 2 drops of water, right? So this method it can be used, but it takes very long time. So why not to change it, to have another test? Okay, now we will go to another. It's called falling head permeability test. Falling head permeability test, or even variable head permeability test. Falling head permeability test or variable. Why falling? Because there is a change. It was fixed, constant, right, in sand. Now here it is falling head. Okay, falling. There is a change in level. Okay, there is a change in level. There is a change in elevation, in water elevation. Variable because it's changeable, right? Variable. So this is used for clay or for fines or whatever, clay or fines. Okay. Now let me see how it is. Almost we have the same components, container and soil sample with A cross-sectional area, A, and with L, okay, and with container here to get the water. But instead of having container above, I have a very small standpipe. You know, in standpipes, any change is remarkable, okay? Any change. So I have a small standpipe. That's why the cross-sectional area here is A small. Here the cross-sectional area A big, A capital, right? Here this cross-sectional area is A small, okay? What is the idea? The idea is, at the beginning of the test, I have water here. Time equals 0. Time equals 0. Height is height 1, say. Okay? Height 1. At time, say time 1. Okay? Now, the test begins. Then water will go down. Okay? After a while, I will have height 2 with time 2, right? And height 3 with time 3, height 4 with time 4, etc. until I have at the end height final with time final, right? Okay? So I can represent the permeability by the change of height versus the change of time, right? And to make it easier for you, I suggest, okay, have the first height, because it's fixed, at time 0. And then the last one, I finish the test, stop the test, I will have the last height, easy to record it, with the time for the test, okay? And I have to go for differential equations. Don't weep. Don't cry. I will make it easy. I know you don't like differential equations, okay? So I'll let you have your dinner, and I'll talk about differential equations next time.